most of people here attended the school in Semинар, so they know Stephen Boyd very well. We had a lot of discussions with him, and I also introduced him at the very beginning. But still there are some who see him the first time. And I want to introduce Stephen, give him some numbers. Okay, so it's about your publication activity, citations, and so on. Just this morning I looked at Google Scholar and found the figures which were fantastic. So for those who don't use Google Scholar or something like Publish or Perish, these are results. How many papers is published by some author, how many citations, that is how many references for these papers, and so-called Hirsch index, which means how many papers there are. Say if you have 30 papers, and for each there are more than 30 citations, your Hirsch index is 30. So let me present typical results. For I choose first Kharitonov B, which is number one in our parametric robustness. We know him very well. So what are the figures for him? So it's Kharitonov. So the total number of publications is 183. Actually it's upper bound, because some papers are in different languages, they are published in different versions, and in Google Scholar all of them are taken differently. So he has 183 papers, including books and chapters in books, and it's pretty large. So now about citations. He has 2,600. Well, these are not precise numbers, but just some impression. As Stephen explained, just two first digits are of interest. Okay, and his Hirsch index is 19. That is, he has 19 papers with more than 19 citations. And it's pretty good. It's a large number. Okay, and for instance, the most famous his paper about Kharitonov, well, of course it's not called, in his paper it's not called Kharitonov theorem, but nevertheless. It has, so the single paper with the largest number of citations is 1,000 citations for this famous paper. Okay, this is for Kharitonov. And it's very typical. It's large numbers. So what happened with Stephen? First, well, I took these numbers from publish or perish. It's the fastest way to get them. And we get the upper bound. So the number of papers should not exceed 1,000. And they said that he has more than 1,000. Okay, so 1,000, more than 1,000 publications. Well, and now it's something incredible. What is the number of citations? That is how many people, how many papers there are which have references to these publications. So it's something fantastic. 78,000. And your Hertz index, it's hard to believe, it's 111, more than 100. And well, the two most popular publications is this famous book, Convex Optimization, and it has more than 12,000 citations. And another one, the book on LMIs also has around 12,000 citations. So I guess it's an absolute record in this field. Maybe for biologists, maybe for some in medicine there are even higher numbers, but in mathematics, in applied mathematics, total Gaussian optimization it looks something fantastic. So still, sorry that I know you don't like such things, but nevertheless, just for you to have an impression who is giving a talk today. Okay, so
okay.
That's all.
You shouldn't trust these things. Well, thank you. So today, I'll, I guess, for some of you who were at the at this meeting, I was only there for the tail end, but maybe you're sick of me by now. But so anyway, today, should be the last talk I'm giving, I promise. Unless there's a problem with my flight, in which case you'll see me again tomorrow. It's about alternating direction method multipliers. This is from a survey paper, or even it's a little book that we wrote recently with some others. And you'll see when I get into it, this is it's supposed to be very readable. It's like a comic book. It's not hard. It's not dense. You just read it page by page. And the idea is there's a few things you learn, and then actually you can do a lot. So I think it's fun like that. And you'll see that most of this is not new. Maybe some of the applications you might technically say are slightly new, but even that I don't even believe. You'll see the methods are all from the 70s and 80s, and even the ideas go into the 50s. So, okay. So the goals are, well, I mean, in optimization, in convex optimization, it kind of goes like this. If you have a problem with maybe 10,000, 1,000 variables, we can solve any such problem immediately. There's just no problem because you use an interior point method, and you use things like LAPACK to do the linear algebra, right? And it just works, period, always. I mean, the actual software people use, sometimes it fails, but basically it just works. You get to problems with maybe 10,000 variables, 50,000, and these you can solve using sparse matrix methods. I mean, that's not your problem. You still use an interior point method, but the interior point method uses sparse matrix methods. And so this works. This is things like Sedumi, SDPT3, and then all these other solvers, right? Then you get bigger problems like 1 million variables and 10 million. And so my experience is this, that anytime anybody ever wanted to solve a problem with 1 million or 10 million variables, they were able to do it, using some method, always, no exceptions. And so we did a couple, I mean, we've done a couple of these. People in machine learning solve huge problems and things like that. And we've done a couple of these problems just to show that it can be done by example. So what I want to, and you can imagine that this goes on and on. So then you say that's how you solve a 10 million variable problem. Then how do you solve a billion variable problem and a 10 billion variable problem? But in fact, I think what's nice about the stuff I'll talk about today is it just basically it says here's how big a problem we can solve. Ready? There is no bound. It's just infinity. So the largest any problem you can describe, I think, can be solved. I mean, this hasn't actually all been put together and done and all that, but roughly speaking, it's not quite a true statement because it's not been done, it's not commonly done, but we're on the way there. And yeah, so this is just not huge scale, you know, ultra huge scale. It's just arbitrary scale. That's the idea. Now, that's going to have to happen on a data center. Right, so that's going to have to happen on 100,000 processors or something like that. But that's okay, and it's going to use a distributed file system and all that kind of stuff, because in fact you can't even describe a problem, just the data is huge, right? So, okay. Of course many people have done distributed optimization, but the idea is that there are some very simple methods which are very robust, right? So, this is something like that. You know, it's something like a subgradient method for sort of small problems. It's simple, it's robust, it's not complicated, and it just kind of works, right? This is going to be the description of that. So, now this comes up in lots of things. It comes up in machine learning and statistics. That's kind of obvious, but it also comes up in things like dynamic optimization on large-scale networks. So, for example, if you're going to schedule energy generation and consumption. You know, you have a big network with 30,000 nodes, and then you have 50,000 devices. You're scheduling for a day in 15-minute increments. That's 100 variables for every device. The lines have capacities, that you have generation costs, all sorts of things. And you put it together, and the next thing you know, you have a billion variable convex optimization model, right? So it's not just machine learning and statistics who have these huge, huge problems. So the method, of course, is optimization. It's an old idea, I'll say something about that. But the idea is that you have entities, you can call them agents if you like, but in fact this could apply at many scales, right? These could be individual processors in a small multi-processor system with 64 cores. It could be something bigger. It could be a data center where you have you're going to fire up 100,000 cores or 1 million cores to solve something. Or they could be actually some kind of devices, right? So I'll describe a little bit about some dynamic energy optimization where literally each device optimizes its own behavior, but they talk to each other to coordinate. Okay, so by the way, it also works at the lower level. These devices or whatever, they can be threads in a processor in a multi-core system. They can be simple threads, or this could be a GPU. And these could be what's done on each GPU processor, and then they'll synchronize and run again. So you could imagine this happening at many, many, many scales. And we've applied it at several, just for fun, just to see if it works. Okay. Oh, and the idea, of course, is each of these things is going to solve a problem. We'll call it a little problem compared to the big one, but it might not be little, right? It could be, if it's a full processor, it could be solving a little might mean a 50,000 variable convex optimization problem, but you have 1,000 processors doing that, and then they'll exchange messages and solve again, right? So, okay. So the outline is this. I'll first talk about dual decomposition. This is a very old idea. Okay, so dual decomposition. This is just, I'll go back and do the history. So first we'll do dual decomposition, then we'll get the method of multipliers. And then this is just historical, this is historical precursor. This is just so you understand it all, and I put everything in a historical context. Then we get to alternating direction method of multipliers, which is an operator splitting method. And then, that's it. This is it. At this point, the talk is over. And it's very simple. You will see. It's something that fits on the slide easily. A very simple algorithm. We'll get to that. Then all we do after this is I'll just go through little bits and pieces to show that this very simple algorithm, if correctly used, can actually then be used to do tons of things. Build fast solvers or solvers at scale for small things, all sorts of other stuff. I'll talk about different things that come up. Then we'll look at a couple of examples. And then finally, we'll get to consensus and exchange. These are two problems, there are two canonical problems in decentralized optimization, large-scale optimization. And if you understand these, then you can understand the more general case. And then if we have time, we may not, I'll talk after this about one example of exchange is actually dynamic power optimization. We may get to it, may not, it doesn't matter. Okay. So I'll go quickly over this because it's, I assume most people know about it. And this is just for the historical background. This is just, it's nothing more. Okay, so you want to solve a convex problem. You minimize a convex function subject to ax equals b. And you form a Lagrangian. You minimize over the primal variable and you get a dual function. And then you get a dual problem, which is to maximize g. And then you can recover this if things happen like, for example, if f is strictly convex, right? Then you can actually recover this. So this statement that if you were to maximize g, you could recover x. There are some technical conditions, and they're not just these pure mathematical conditions. This would actually fail in lots of problems you'd like to do. A very common example would be linear programming. So linear programming, you can't really, I mean, you can, but it's not this simple. Yeah.
You don't have any other constraint, just linear ones?
Well, let me explain that. By the time we get going with the talk, we're actually going to allow f to take on the value plus infinity. So and then at which point all constraints will fit into f, right? But for now, this is just the historical background. Okay, so how do you solve that dual problem? Well, you just apply a gradient method, right? Or a subgradient method if the dual function is not differentiable. And what you do is you simply take a gradient or a subgradient, and you take a step. And it turns out that the gradient of the dual function is nothing but the residual for the linear equation, right? And so dual ascent, and remember this because you're going to see this for the rest of the talk. It's got two parts. In the first part, you fix this dual variable, or price vector, or whatever you want to call it, and you optimize over x. You fix the price vector or dual vector and you optimize over x. That's your next x. And then at the next step, you update the dual variable and you do it by looking at the residual. And the idea is that you will drive the price vector to the right value, at which point this will be 0, and that means you've solved the problem. So this is the idea. And I mean, this is an old idea. And this works, but there are lots of assumptions that you have to make here. Okay. Here's the main application of this. So the main application is this. You take f that is separable. So these are vectors. So x decomposes into blocks of vectors here. And then f is separable. It's a sum. Now, of course, if the equality constraints were also separable, the whole thing would be silly or something like that, right? Well, it'd be fine. It would just be a trivially parallelizable problem, right? But so presumably, the objective, these x's are separable, but the equality constraints couple them, right? So, but if you do this, and you form the Lagrangian, then that's this thing. But this thing is separable in x, because, this is a constant, and each of these looks like that. And so the idea is this. When you do the x minimization of a Lagrangian, when f is separable, it separates like this, and that means you can carry these things out in parallel. And that gives you this method here, very famous, is dual decomposition. And so the idea is the following. You have a common dual vector or price vector. You scatter it to all of the little entities, and then they minimize. Completely separately, and this is done independently and in parallel. Then you collect all of these partial responses, sum them to get the residual, and then this tells you how to update the dual vector. Right? So this is classic. This is from 1960, 1960. The truth is probably people knew this earlier. So I mean, that's the idea. So this is not new.
May I also add one more name
Sure.
to this list? It is Shor, who suggested in the beginning 1962,
Oh, okay.
he applied it to linear programming, actually for transportation problems.
That's right.
And then it was
okay.
not gradient method, but
Subgradient.
method.
Subgradient. Yeah.
So it was the first application
I
of
will add it. Next time I give this talk, it will be there. Okay.
Because it's actually the same
I'm- It's the same. Yeah. Yeah, I'll do that. Okay. So the idea is you're now solving a large problem by, you solve all these subproblems in parallel, and then you collect, you gather. That's a gather right here, or an all reduce, if you know what that is. That's what it's called in sort of the modern language. And then you scatter the y, right? And this works, but it's with lots of assumptions and it's often slow. Okay, now we get to the 70s. So this is all just, we're doing the history to see how it all connects, okay? So here's method of multipliers, and the idea is it's a method to robustify dual ascent. And this, again, goes to the 60s, at least the 60s, and the idea is that this is the usual Lagrangian, and you add this. By the way, this is nothing but the Lagrangian for the problem where you add an additional, you say minimize f of x plus this, subject to ax equals b. They're clearly completely equivalent because the thing you're adding to the objective is 0. So there's nothing sophisticated or complicated, or you don't have to analyze it again or anything. Now, and you can give a nice interpretation of what this means, something like that. And this leads to the method of multipliers. It just looks like this. You fix the dual vector y, you update over x, and then on the next step, you calculate the residual, and you use that to update the price. Now here there's a very specific step length, which is rho. Okay? And I think maybe what I'll do is not explain the step and just move on so we can cover more material. In fact, probably people know these things. All right, so there's good and bad news. The good news about the method multipliers is it converges on, so the dual, something like the dual gradient method requires lots of assumptions, and they are real, right? It will just fail completely for linear programming and all sorts of other things. It's just, these are real things. These are not just little subtleties, right? In comparison, the method of multipliers works always. There's no exceptions. It just works. Yeah?
For linear programming, does it work?
Which?
For linear programming.
Perfectly.
When function f is linear.
Works perfectly. Yeah. I'll tell you what it is. It's f. The function is linear plus the indicator function of x being non-negative.
That's better.
Yeah.
Sure.
Yeah. Then it works perfectly.
But the first version of algorithm doesn't work.
Which is the first version?
Without rho.
That's correct. It doesn't work. That's right. Yeah. So with rho, it works. Without, it fails completely. Yeah. It's strange. Well, the reason is the Lagrangian is affine in x, and you can't even minimize it. It fails on the first step. So.
And another good news is that it converges fast.
This converges fast. But the amazing thing is it actually works. F can even be an indicator function, and you're going to see later most of the applications. F is an indicator function. It's a function that's 0 to plus infinity, and these are things that would make these other things fail completely, right? So that's why I don't write constraints throughout this talk. I don't write constraints explicitly because constraints are nothing but functions that take on the value 0 plus infinity. That's all. Okay. Now the bad news is. When you do this, you can no longer do distributed optimization, which is what you wanted to do in the first place. Okay. All right. And that brings us to the topic, which is alternating direction method multipliers. And the idea is it sort of combines both things. And you can think of it as robust dual decomposition or decomposable method of multipliers. And it was proposed, I think nominally, at least the Western take on this, is it was proposed by these guys in '76. It turns out it was later shown to be absolutely identical to operator splitting methods that are from the 50s for PDEs. And I know actually there's a Russian version too, and I know what that is. I know what it looks like. It looks different, but it's actually very close. So let me write it down. So here's the abstract form. Actually, now the talk starts. Right? So if you start paying attention now, And you should start paying attention now. Because if you pay attention for the next 15 minutes, maybe 20, you will actually learn something that you can actually apply like immediately, like this afternoon or tomorrow or something like that for problems you need to solve. I mean, it's a weird thing. You'll see. So, for example, you can write a 4-line LP solver. May not. Actually, the funny part is it probably won't be that uncompetitive. It'll probably be pretty good. So, okay. So it looks like this. You simply split the problems into two parts. I assume the variable, which I now call x comma z, and I split it into two parts. The only thing I assume is the objective is splitting across these two, right? So, and then that's a completely arbitrary linear constraint linking them. That's it. So it just splits two ways. By the way, the Russian version of this splits it into k things, not two. Okay? And I've read these things, but I forget what they're called. Doesn't matter. Yeah, and actually, you'll see, although we're splitting by 2, we can split into arbitrary things as well. You'll see. Okay. So the augmented Lagrangian looks like this. And here's the algorithm. This is the entire algorithm. That's it. Now it works like this. It says this. Now, method of multipliers would be to minimize this function over x and z jointly. That's method of multipliers. That works unbelievably well. Instead, you do exactly one Gauss-Seidel sweep. You minimize over x, then z, but using the updated x, and then you do a dual update. Okay? It's very simple, the whole thing. Very simple. Okay? Oh, by the way, for those interested in control, if you take a look at this, what you see is the following. That's an error, right? It's a residual. But let me just call it an error because then it sounds like something in control. And if you look at this very closely, in control, that's an integrator. And do you know what this is? This is PI control. It's nothing more, right? Operating on a monotone operator. It's PI control. So, by the way, if you make that claim, this goes back to 1905, okay, or something. Well, okay, at some point this gets silly, but the point is, it's very simple. There's integral control right there. Okay. All right. So I think I already said this, and I think I'll skip this, which is some of the details. But I'll point something out. If you need to minimize, this is a linear term plus a quadratic. But you can combine a linear and quadratic to make a single quadratic, right? So it's the same, minimizing this thing is the same as minimizing that, where u is nothing but a scaled dual vector, right? So we'll write the algorithms both ways. It takes less ink if you use u, but remember when I write it this way, I could just as well write it this way. And we'll switch back and forth without saying anything at all. So you'll either see it look like this, and then this is the thing that causes this thing to converge to the right value. And over here, it's this dual variable that causes it. But they're the same. They're just scales. Okay? All right. So here's the convergence. The executive summary is it works always. Period. So in fact, you can make a very strong statement. It's this. You assume f and g are convex, closed, and proper, and there exists a solution. I mean, if there doesn't exist a solution, then there's nothing to do. Okay? So I can't think of anything less you could assume. You cannot assume less.
What do you mean by proper?
Proper means it's not always plus infinity. So that's kind of stupid, right? Oh, by the way, I can handle problems where either f or g is always plus infinity right now. Right? So the solution is it's unsolvable, right? So, I mean, these are just really stupid. I mean, this is the minimum thing you can possibly have. So basically, it says it works always, and no exceptions. And here are the actual statements. Now, normally, when you give a talk and you have slides, you're allowed to lie. In other words, you can say things that are not true because there's some technical conditions, and you don't want to put all the technical conditions on your slide because it's unattractive, and everyone know what I'm saying here? So anyway, so there are people who put all the conditions on the slide, and it's silly, it's stupid. That's what papers are for and things like that. So on the slides, you should feel free to lie. A little bit. Right? So, okay. However, in this case, these are just true. These are not lies. These are just true. So here are the statements. They're chosen very carefully because I can tell you some other things on here which are false. So here they are. The first is that the residual goes to 0. So as you run the algorithm, the residual goes to 0. And the second is that the objective approaches the optimal value. These two hold with no assumptions whatsoever on A, B, C, nothing. No assumptions at all. Nothing. No assumptions on the initial problem except that it has a solution. Okay? By the way, you do not need anything more in practice than these two things because this is what would cause you to quit. If you're running an algorithm, you will stop when the following is true, when the residual is small, and when the objective is near the optimal value. Right? So you need nothing more in practice. Now I'll tell you some things down here that we didn't say. Oh, there's one more thing that's true. Here's one thing that's true. Y converges to an optimal dual variable. That's true. Okay. Now here are some things that are false. Ready? That X converges. Doesn't even have to converge. Z converges. That's false. And then even more false would be X converges to an optimal value, Z converges to an optimal value. But these are irrelevant, in my opinion. They're completely irrelevant because they're interesting things in theory and they're totally irrelevant in practice, in my opinion. So that's it. So this is the idea. Okay. All right. Now it turns out this algorithm, I call it ADM. Well, I'm referring to it as ADMM. It turns out is absolutely identical to operator splitting methods. Something called it's Douglas-Radford splitting. It's identical to it. By the way, it took something like 20 years before anybody figured that out because the algorithm is complicated enough that you write it the right way, and it's not that easy to see that the two algorithms are the same. It's true. It's not that easy. But it's the same as many other things, and these go back into the 1950s. These are methods for PDEs. It's got other names. It's something called Dijkstra's alternating projections, Spingarn's method, progressive hedging, proximal methods. There are some new methods where instead of with a quadratic, you would augment with something, a Bregman divergence, right? It makes it sound fancier, but it's basically the same thing. So all of this says, I'll continue to call it ADMM, or alternating direction method model, but in fact it's absolutely identical with Douglas-Radford splitting. Period. It's absolutely identical, and it's very close to many other things. Okay. So now, by the way, you know that you've seen the algorithm, right? I mean, there's nothing more, and there's nothing more to say, right? Where's the algorithm? There it is. It's right here. You form this Lagrangian. You do a step in X, step in Z, update Y. That's the algorithm. Okay. I mean, there's some variations on it. You can vary rho at every step, and you can do over-relaxation. But this is the basic thing.
Excuse me.
Yeah.
Bro, is it given in the problem? Or
Nope. Nope. It's a single problem parameter.
What is this?
It has to be positive.
What is that? So
That's it.
Medium,
Yep. It could be a million.
one.
Could be one. You can keep going. Yeah.
No, it's not strange. The rate of convergence depends on...
Absolutely. And we'll talk about rho
the
later.
convergence in itself...
It does not. Yeah. So we'll talk about rho later. Okay. So, all right. So all we're going to do now is make a short catalog. Oh, by the way, so everything comes down to this. At every step, there are two steps of the algorithm, and then you update. Okay. So the only thing you have to do. And actually, I think this is extremely interesting because it's a completely different interface. It's a meta interface for optimization. I'll explain that in a minute. The only thing you will ever do in this algorithm is you minimize a function plus a quadratic. Now remember, these functions can be plus infinity, so they can include constraints. They can be pure constraints. Pure constraints is a function f, which is 0 on a convex set, and plus infinity off it. Okay? So, but the point is that the only thing you ever do is you minimize a function plus a quadratic, period. So, by the way, this is completely different from the interface you have to other optimization methods. In other optimization methods, the interface you have to a function is you evaluate a gradient, a subgradient, a gradient and a Hessian of a barrier function, right? You can think of lots of other interfaces. And then you get algorithms that are very low level. They involve gradients and subgradients and, you get Hessians and all this kind of stuff. This is very high level. Okay? So, it's a way, every step it's a meta optimization step because each step involves an optimization. Many cases we can carry it out analytically, but that's not the point. So, okay. So the idea is we're going to look at special cases when you can solve this quickly or how to do it. So the first one is trivial. If F splits, if it's separable, and A, is also conformably block separable. But then the X update splits. So there you get parallelization for free, right? So if you want to calculate this quadratically augmented minimum and everything splits, it's for free. Okay? So this is obvious. Now, a lot of problems have either A equals I or B equals I or something like that, in which case this has a name. When you minimize a function plus this distance to some given thing, that's called the proximal operator here. So, and there's a lot of beautiful theory about this. It's basically you take the conjugate of f and you add quadratic regularization to it, and then you conjugate back or something. But the point is, it's just this. But let's look at some special cases. Suppose f is the indicator function of a set. Then this is either 0 plus infinity, and for this thing the row doesn't matter, and this is nothing but projection. And that's the idea, is the proximal operator is supposed to be a generalization of projection, right? And in fact, if you know about monotone operators, that's kind of the idea. It's like it's a monotone operator. Here's an example just for fun. Suppose this is the L1 norm. Then, by the way, this separates down to the component, and you can write it this way. It's just soft thresholding here. So in other words, if this is an L1 norm here, and I calculate this proximal operator, then all you do is you make this function that looks like this, right? It goes like that. Or for you, it goes like this, like that. Okay, so it's soft thresholding, and we'll see there's lots of others. They're actually fairly simple. Okay. Now, if you had a quadratic objective and you have to minimize a quadratic plus a quadratic, well, that's silly. That's minimizing a quadratic. You get an analytical solution. It's just this. Okay. However, and this is very important, and actually this is something where, anyway, I think this is very important. It's this. Oh, first thing is, you can solve this depending on the structure of P and A and everything. You can use matrix inversion lemma. This is kind of what people trained in theory, this would be as far as they would know. The truth is the following. If you want to solve that using a dense method, what you really should do is set up the KKT system and solve it via a modern LDL transpose solver. Okay? And that will exploit all possible structure in it. That's the correct way to do it. This is very important, and something I think people trained in sort of pure theory often don't know or don't appreciate even if they know it. It's this, and it's far more important than anything involving sort of the complexity of the algorithm, the number of steps to achieve an epsilon solution, all of that. This is far more important. It's the following. You have to solve this every step, and that means that you actually have to solve a set of equations with different right-hand sides every step. Okay, so, I mean, this is an important thing. The correct method to solve AX equals B, well, I'll just ask you this. Suppose on my laptop, it takes me 1 second to solve AX equals B. That would be for about 2,000 equations. So I can solve a 2,000 by 2,000 equation in 1 second on my laptop. Okay? How much time does it take me to solve 2? Same coefficient matrix, 2 right-hand sides.
So, what do you mean now there are 2,000? So
Nope, I have 2,000 by, I have A is 2,000 by 2,000. I want to solve AX equals B. And then that takes me 1 second.
You solve it twice.
Yeah, and now I'm going to solve AX1 equals B1, AX2 equals B2. How long does it take?
The same time.
1 second. That's the answer. Everybody got that? You didn't answer fast enough, which leads me to suspect that you don't appreciate this fact enough. Okay? So, and the reason is this. The first time you solve it, you factorize A, and that's order n cubed. Okay? Then you back solve. That's order n squared. Okay? If you have to solve a second system with a different right-hand side, you only do the back solve. And it's order n squared. And that tells you immediately, it says once you factorize, you get a discount of n every time you solve. Everybody see what I'm saying here? So, and we want to do this for big things, so that's not a small number. Okay? So, okay. So in a direct method, you cache factorizations, and you will get a huge discount after the first step. Okay? Just for free. Okay. Now, if you're using an iterative method like LSQR or CG, you use warm start. Because after a while, the algorithm is converging, you're almost converged. Then you have to call the solver to solve this, but you start from the previous point. So basically, the iterative solver has state. This will give you unbelievable speed up. right? Because it's very typical for CG to take something like, I don't know, a couple hundred steps on the first one, 50 on the next, and then in the end game, it's taking 5 CG steps every time. Everybody see what I'm saying? And each CG step is very cheap, right? So, again, these are things. By the way, these comments make it kind of is another reason why focusing entirely on like the number of iterations required to solve a problem, at least in this case, is completely silly. Because the iterations can have costs ranging over 1,000 or 10,000 to 1 ratio. At which point, counting iterations is not appropriate, and that should be clear. Okay. All right. Now, if you have a smooth objective, you can use anything you like. Gradient, Newton, quasi-Newton, limited memory BFGS, doesn't scale to very large problems. By the way, when you have a smooth problem, the only problem with something like CG or BFGS type methods, the only problem with them is when the function you're minimizing doesn't have enough curvature. That's when you get into trouble, right? But here you're adding quadratic curvature, right? Because you're adding the curvature, that makes these methods work perfectly, just unbelievably well. And in fact, in this case, the old idea, this is from the 70s, is here's how you select row. You select row to make these problems easy. So if your BFGS is taking more than 20 steps to solve, increase row. That's the algorithm. Okay. Now here, of course, you do things like warm start. Okay. And now so my claim is you don't know it yet. But if you just combine the handful of things I just told you, you now actually can do a lot. You can construct algorithms, and it's by, you take your original problem, you transform it to this form with x and z, apply the very simple things, it's nothing complicated here, nothing. And you will actually now get algorithms that distribute across processors. Even on a single processor are unbelievably fast because of factorization, caching, things like that. Let's do examples. So let's just do generic unconstrained problem. So we say minimize f subject to x and c, and we're going to rewrite this problem this way. I mean, it's completely, there's nothing there. In fact, it looks like when you rewrite this problem, so the equality constraint is x, but notice actually conceptually how interesting it is. What this says is, I'm going to write this problem this way. I'm going to write it as the objective plus a second objective. But this objective is an indicator function. So in fact, G does nothing but encode the constraints. Okay? But the nice part is they're separate. I've separated the objective part from the constraint handling. Okay? And then the constraint, it's a very silly constraint. It just says the two have to agree. Okay? And the algorithm looks like this. On the first step, I minimize f plus g plus this thing, but I'm minimizing over x, so the g doesn't matter. So you just minimize this. So all you need to do is you need an oracle that minimizes, that's a proximal operator. So it says x's updates under a prox operator, right? And then you project onto the set, and then you update. There's your integral action, right? This is your error. That's your residual. That's your error. And u is the integral of the error. So this is integral action in control. Okay? Nothing more. Okay. So now, by the way, this has the same components as something like projected gradient. Oh, and by the way, if rho gets really big, this is a gradient step. Just for the record, right? So this is like a gradient. This is like a gradient, a projected gradient step, except one big difference. You actually have an integral here, and so that's actually going to give you much faster convergence. Right? Here's an example. It turns out, for example, that in fact this would do linear programming instantly because this is just linear. That's C transpose X, and then C. Well, you can do whatever you like. Or here, you can split it many ways. Linear programming.
Here, no, it said C.
Yeah.
There, no.
That's what?
Yeah, no, we have no set.
No, it can be reduced.
Yeah, here I had a set here, and I'm just putting it here, right? So the point is though that in the code you handle the objective and the constraint completely separately, and what happens is they come into consensus. So when x is equal to z, that means they both agree on what the variable is. So that's So it's very simple. This is much faster. For example, if that's polyhedral and that's piecewise linear, this has finite convergence. Finite number of steps, it converges exactly. Okay? So, by the way, you might ask how many steps is that? And it's exponential. But, you know, you shouldn't take these theoretical results too seriously. You kind of take them as a flavor, right? Isn't that nice? So, okay. There it is. Let's solve another problem. How about lasso? So, here, you minimize. This is very popular in modern statistics, machine learning. So this is ordinary regression plus an L1 regularization, Landa's posse. Okay? So, again, notice that these splittings that we're doing are completely stupid and trivial. They're not sophisticated, right? So here, all we do, in fact, and the idea you should get into is this. You look at a problem and you ask yourself, do I have a good way to carry out a prox operator on that part? And for quadratic, yes we do. And for L1, sure we do. So you split them. In other words, instead of having one variable x, you have x and z. And you have the stupid constraint x equals z. It's very simple. Okay. So what's the method? Well, if you do a proximal update on this, you get this. This is soft thresholding, so that's nothing, right? And then this is also nothing. That's your integral control. Okay. So, but you look at this more closely and you realize, hey, I can do factorization caching for that. Okay. Okay. Very simple, right? We just turn the crank. Let's do an example. So here's a problem with a matrix that's 1500 by 5000. So it's 1500 measurements, 5000 regressors. Oh, by the way, I'm sure you know there are like 5,000 papers on how to solve lasso, right? I personally have written 3 of them, or something, right? So, I mean, there's thousands of them. In fact, just within 100 meters of my office, we could probably account for 100, because there's people in statistics, people in computer science, and all that kind of stuff. Okay, fine. So, no problem, right? Okay. So, for this problem, and this is MATLAB, so it's kind of silly. If you simply do this here, except the only thing you have to do that is one extra line is you save the factorization, you cache the factorization. If you cache the factorization, here's what you get. By the way, the cost of a factorization is the cost of a least squares problem. In statistics, it's ridge regression. That's 1 second. Subsequent AEM iterations, by the way, this is wrong. That's 30 milliseconds. And this is wrong, and I can tell you why. You should have gotten a speed up of about 500 to 1, and this is less than, this is a bit more, it's not as much speed up as you want. But come on, it's a 7-line MATLAB script, right? Then the lasso solve takes about 3 seconds because it takes 50 steps. But here's an interesting thing. When you solve a problem like this, you actually go back and you vary lambda over some range, and then you choose the correct lambda by cross-validation. That's the correct way to do it. Okay? So if you do that, notice that once I factorize this, I can solve the problem again for a different lambda, and it's cheap, right? Because each step is 30 milliseconds now. Everybody see what I'm saying? So these are, yeah, that's. So here, for example, I can solve 30 of these problems in 4 seconds. This is a 6-line script. It's nothing more. So I have to admit, honestly, that when we wrote interior point methods and other things for these things, we did not know that there was a 7-line script that would come close to this. Okay? So, by the way, it's a beautiful thing because there's a standards idea in convex optimization that goes like this: that you can solve a convex optimization problem in not much more effort than a least squares problem. That's this. It's an idea. Okay? And the idea goes something, and you justify it this way. You say, well, look, you use an interior point method. What does an interior point method do? Well, it takes 20 steps. Okay, maybe 30. Each step is actually solving the least squares problem, right? So that would be the idea. So at a cost of 10 or 20x, you can solve 30x. You can solve a convex optimization problem at 20 or 30 least squares problems. What's interesting is that's perfect here, except the multiplier is often like 1 or 2 or something, right? Notice also how completely irrelevant counting the number of steps is here, right? If the first step costs 1.3 seconds and subsequent ones cost 30 milliseconds, and this is a small problem, right? This tells you that counting steps is a little bit on the silly side, frankly, right? So I'm mentioning that because I know many of you, have that training, so I'm just mentioning that. Okay. Let's do another one that's a little bit more modern. Again, it's just a few things. I have an empirical covariance of some samples from some Gaussian, and sigma inverse is sparse, right? And that means it's a Gauss-Markov random field, or rather, right, because the inverses in sigma, the zeros in sigma inverse correspond to conditional independence, given the other variables, right? So your job is this: given samples of something, you want to discover the structure of a Bayes network in, I guess, a Gauss-Markov random field, right? So, and to do that, you write down the negative log likelihood function, that's this, right? And by the way, if you minimize this without this term, you get exactly sigma equals, or rather, sigma inverse equals S inverse, right? That's it says the maximum likelihood estimate is the inverse of the empirical, or it's equal to the empirical one. Okay, but you add this, and what this does is it sparsifies X. X is the inverse of the covariance matrix. And then this is relatively recent things, right? Here's some methods. There's covariance select or something like that, and this is from Hasty and I forget, Steve Shirani maybe, and I don't know, Friedman maybe. So these are my colleagues in statistics, right? So this is the problem you solve. By the way, if you type this into CBX, it will bring CBX to its knees if the problem is more than like 30 by 30. The reason is very simple. Things like this are handled very efficiently by themselves because you end up solving a dual or something like that. But the minute, if you mix matrix constraints with element-wise constraints, forget it. Right? It will solve it. It will just take a long time. Okay? So, and if nothing else, this will solve a very practical problem for me because I go lots of places and people say basically not this problem but something like it, and they say, oh, it doesn't work past 30 by 30. Help me. And so now I have a common answer for this. Okay, so let's do it this way. Let's split it. We split it this way, and notice how silly our splittings are. Right? Our splittings are silly. What we do is we take the linear form log det. And then we have the one norm. We know how to handle that, so we split it this way. And in the first step, you minimize this thing. In the second, you do element-wise thresholding. Okay? Now, this one is interesting. You could look at that and guess that there's going to be an analytical solution. And the reason is kind of clear. It's because all of these are unitarily invariant. Right? So, in other words, look at all of these. Every term is unitarily invariant. That means I can diagonalize and solve it there. Right? So that's how this works. So and in fact, here's the analytical solution of something like this. Then is this: you diagonalize this thing, and then you find the eigenvalues and you solve a quadratic, and then you get this. So the cost of an X update is an eigendecomposition. Okay, and so here's a case with 1,000 by 1,000 with 10 to the 4 non-zeros. And these are sort of, rather complicated, state-of-the-art things. And these things can take 20 seconds to 3 minutes, roughly. We wrote a script that's about 8 lines, developed it in about 4 minutes. It's not the same, but it's sort of in the ballpark. It's quite close, right? And it's better actually than this one, which was the first one for this. So. It's just, all I'm showing you is you actually now know, you can actually assemble things now that you couldn't do, or you can assemble a solver quickly. Okay, now we're going to go to distributed optimization. So the simplest form is consensus. So consensus works like this. And it's really silly. It says, I want to minimize a sum of functions of a variable. Okay? And by the way, now that we understand that these FIs can be plus infinity, this could be splitting out the constraints. This could literally be F0 plus the indicator function of all the constraints. So I can just treat each constraint separately or however you want to do it. Right? By the way, in statistics or machine learning, this could be the negative log likelihood loss, or a loss function for the ith block of data. Okay? In which case, this would be called collaborative filtering, because you would have a block of data, you'd have a block of data, I'd have a block of data. It's huge. Each of these is a petabyte. We have no intention, we couldn't even send each other the data, but we're going to agree on a common statistical model, and we do that this way. Okay, so ADMM form, again, it's not complicated. In fact, it looks ridiculous. Here it is. You take this, and it's a very subtle change. The first thing is you let each agent or box have its own opinion as to what the variable is. Okay? Then you insist that everyone can have their own opinion. However, they all have to match the global opinion. So, okay, that's the idea. And you would call these local variables. That's the global variable. These are called consensus constraints or consistency. Okay? So, it's not complicated, right? It's very simple. Okay, so you just turn the crank, and it goes like this. The Lagrangian is you add up these things. And ADMM looks like this. This step can be done completely in parallel. You will do a prox step on each of the f's, right? And then in this step, you minimize this Lagrangian over z. But you know, if you minimize over z, that's irrelevant. You're minimizing a quadratic, and it's nothing. It's an average, right? Actually, it simplifies because these things add up to 0. And it turns out the algorithm is even simpler. It's this. And it's a very beautiful algorithm for consensus. It's this. It says, at each step, you minimize your local private cost function, or constraints, whatever it is, plus the dual variable, your dual variable times, you don't need this, but you know, that's the dual variable term, and then plus a cost, or an L2 regularization, where this penalizes your moving away from the last average. And this makes, it makes perfect sense, right? Because if I send a message to this thing at some point and said, time's up, give me your final answer. If you had an xi, you had an xi, and I had an xi, we would take these three and we would average them. And by Jensen's inequality, that would be better than any of ours alone, or something like that, right? And so, it wouldn't be better, but who knows? It wouldn't be worse than any of ours alone. So we'd average them, and that would be our estimate. So this is something like the best estimate of the answer at step K. Okay, so it's incredibly simple, right? And it requires a gather and a scatter. In fact, it's not even a gather. If you know about these sort of sophisticated, modern, large-scale computation frameworks, that's actually called an all-reduce. It's an all-reduce. So in fact, gather is not even correct. Because, for example, it would be completely incorrect to gather 1,000,000 vectors, each of size 1,000,000, in one place, because you can't store it. It'd be a 1,000,000 by 1,000,000 matrix, and then start adding that. So in fact, it's an all-reduce. You want to form an associative operation on 1,000,000 vectors, and then that would actually happen this way. If one processor were running 5 of these, they would be added together. Then, in the same rack, they would be added together. Then, these things would, someone would make a spanning tree. Now, you wouldn't do it, right? This would be done automatically in the software, and so on. So, I guess we like to think of it as a gather, but it's really an all-reduce. Okay. Then you update these things, the dual variables locally, and then you update the xi's. That's it. So it's actually quite cool. And notice that it just works, right? This tells you that you can now you can distribute a convex optimization problem, the terms, but the terms can be constraints, whatever. So for example, we can now do linear programming, right? We can even split it multiple ways. We can have one processor handle the objective, which is C transpose X. Another processor handles AX equals B. That's a constraint. What do you have to implement for that? It's completely simple, right? You have to make projection onto AX equals B. That's simple, and you do factorization caching. Okay? A third processor can handle X positive. There's many other ways to split it, but handling X positive is nothing. It's a single little line. It's a single line of code, right? And then it'd be weird. You'd have three opinions about what the solution is, right? The objective would have an opinion X1. You'd have another opinion which satisfies AX equals B, and you'd have a third opinion which is non-negative. And then you just run this algorithm, and they will converge. By the way, for LP, this would probably work quite well, and it would also be about 5 lines. Right. The nice thing about this is I can distribute it across processors of my class. If I want to solve a dense LP, we've done this just for fun. If you want to make a dense LP, I have a completely simple way to do it across tons of processors. So I just break up the equality constraints and the variables and all that kind of stuff. Okay. So there's a beautiful statistical interpretation. That's this. If fi is the negative log likelihood function for a parameter x given the ith data block, then what's beautiful, it's absolutely beautiful. The only thing you ever do is this. You minimize this negative log likelihood function plus a quadratic. But a quadratic is the negative log likelihood of a Gaussian. And this is MAP estimation. It's maximum a posteriori probability estimation. So this says that the only thing you do is the only method you have to implement for if a bunch of us we each have some block of data and we want to do joint estimation of a parameter, the only method we have to implement is the following. Each of us has to implement a Gaussian map method. And then all that comes into you is the mean, is simply the mean, because we agree on what the variance is. In fact, the covariance is that. Right? So the only thing that happens is I send you the mean. You do whatever you need to do privately to come back and say, this is, if that were the prior, this is what my posterior would be. And we all do that, and we update, then the integral action here, right here, updates the prior. Everybody says, so it's actually quite beautiful. It says, it's how do you make, you can do completely arbitrary joint statistical estimation, and you only need to implement one thing, which is a map estimator for everything. It's actually beautiful. Not one of us has to even divulge how much data we have, what our measurements are. Nothing. Absolutely nothing. Okay. Okay. So let's do an example. It's going to be a classifier. So let's make a linear classifier. So the classifier is this. I'm just going to. You're going to be given a bunch of feature vector and then Boolean outcome pairs, labeled outcomes. And you want to make a linear classifier that looks like this. This is the margin. And you want the margin to be positive. If it's negative, then you have a misclassification. You have a classification error, right? So you want this positive. And this is homogeneous in W and V, so we can actually arbitrarily say, well, we don't even need that. We'll just go. We make a loss function. I give a loss function here, and it looks like that. And the loss function should be small or 0 for positive, and negative and growing. Sorry, it should be positive and growing for negative, if you have negative margin, right? So, the loss functions basically look like that. That's one. That's called hinge loss. Another one is this log 1 plus EPX, get probit, exponential. And then all of these, depending on what regularization you add in, you can now construct about, I don't know, half of machine learning methods, right? You get support vector machine, logistic regression, you go on and on and on. You get most of them this way, many of them. Okay. And so what we're going to do is we're just going to split the data and use consensus to solve it. This is a baby example, just so you can see it, so I can plot it. So we're going to do support vector machine. So you have a hinge loss, and you have L2 regularization, that's support vector machine. And we have a little baby problem with 2 features in the 400 examples. Now, to classify things with 2 features and 400 examples, you use your eyeball, right? You plot green and red things on a page, and you draw a curve with your hand on it, and you say, that's my classifier. I mean, that's the right way to do it. So, but the point is, this works when there's 25,000 or 100,000 regressors and a lot of data. So we're going to split these into 20 groups, but we're going to do it in a really sick way. Each group is only going to see all positive or all negative. So let's suppose this is a spam filter. Each block of data, everything is either all spam or no spam, right? So not one of these blocks of data alone could possibly come up with a reasonable model, right? Well, in fact, by themselves, they'll come up with a very simple model, which is if everything you've ever seen is spam, and someone asks you to make a classifier, you write the following. Here's my classifier. Ready? It's return spam. That's the code. Okay. So they're going to have to collaborate. Okay. So here it is. And you'll hear the greens, and here's the blues. And obviously you want something that goes like this or something. I don't know. So these are all the different classifiers. Actually, this is actually iteration 1. We should even show iteration 0. But this shows all the classifiers. And of course, they're terrible because each of these things have seen totally skewed data. This is the average, which embarrassingly is already better. That's just Jensen's inequality working for you. You run ADMM. Here's 5 steps. And after 5 steps, these are the local, the private ideas of what the classifier is, right? And you can actually see something quite. What's amazing about this? I mean, let's run it a few more steps. There are 40 steps, and you get the solution. But I mean, again, it's a tiny problem. But what you should understand is what happened here. I have, in this case, 20 groups of data, 20 blocks of data. Not one of them has any idea how many other blocks of data there are. They have absolutely no idea. They support a simple Gaussian map protocol, which says they pass in a Gaussian prior, mean comes in, and they say, if that's my mean, they send back what they think it is. And then they do this, 40 steps. They've been brought to the consensus, and not one of them has any idea what the others are, how many there are, or anything. So, in fact, if you want to get a little bit pedantic about it, you could even say this is privacy-preserving collaborative filtering. Because none of them had to reveal their data. Okay.
And what was the loss function in this case?
The loss function is hinge loss. So it looks like this. If this is the margin, it goes down to 0 at 1, and then it's 0. And then the regularization is least squares. Tick it off. Okay. Let's look at a real example just for fun. Actually, it's not a real example. It's just to show off. But just to show that it's not, you take a real size problem. So we went to our friends in statistics and we asked them, what would be the largest lasso problem anyone would ever solve for any reason? And then we made it like 10 times bigger, just for fun. So here it is. So we took a matrix that was 400,000 by 8,000. Oh, by the way, we've subsequently done things where it's 400,000 by, I think it's something like, over here, something like 20,000 or something crazy. Anyway, just for fun. So we took a matrix like this, and just the data is 30 gigabytes of data. But I mean, actually the point is here, we ran this on 10 machines. We could have run it on 1,000 machines like that, except for one thing. The taximeter would have been running much faster. But I can tell you how much this thing costs. I think this costs something like 30 cents to run this. Okay, so we wrote a solver in C using MPI and GNU Scientific Library. It's completely unoptimized, so everything is a factor of 10 slower than it should be. Right? No Atlas, nothing. Not MKL, nothing. So we could instantly make this 10 times faster. That's not the point. Right? So we then did this. We split into 80 subsystems, and we ran this on just 10 machines. So 10 8-core machines on EC2. Right? This is the Elastic Cloud 2. Right? So I think it cost something like 30 cents to run. I think it might even been less, but anyway. Of course, while you're debugging it, you run it up anyway. So that's another story. But here's some times. It takes 30 seconds to load the data. The factorization, by the way, is equivalent to solving. By the way, you could not factor this in 5 minutes. That's factoring you divide this by 80, so that's 5,000. That factorization is a 5,000 by 8,000 factorization. Right, so that's what it would be. Subsequent iterations are coming in just where we thought they would. You went from 5 minutes to half a second, right? And again, you see how pointless it is in this situation to count iterations. The first iteration is 5 minutes, and it's all over. And well, this was embarrassing. We tried to generate some data where it took longer, but we could. It was hard to do. So anyway, all right. So, and the point is, what's beautiful about this is, that's the time it would take to solve a least squares problem of this size on a parallel system with 80 processors, right? That's what this is. This is essentially solving the least squares problem in parallel on 80 cores. Then someone says, how long does it take you to solve the convex problem? And the answer is the same, right? So it's that same story all over again. In fact, there's no cost here, just none. Hey, this is just to show that you can actually do this. Oh, I should mention that for these things, we have pedagogical software. Everything's on the website for this thing, right? So people write us all the time and say, oh, I sped this up by a factor of 100, and we're like, fine, we don't care. Because ours was written to be short and clear, right? So there's nothing. All right. Now we get to exchange. And I think I'll just say a little bit about this, and then we'll I can ask you whether we continue or not. So the exchange is the dual of consensus. So actually, consensus is the following. It says minimize some f of xi, fi of xi, subject to, you have to listen carefully, X, that's the big vector all stacked together. X is in the range of I, right? That's the, because if you're in the range of I, it means all your subvectors are the same, right? Okay, so this says minimize sum Fi of Xi. If you want, put a star there for the conjugate. So minimize Fi star of Xi, subject to, this time, X is in the null space of I, which is the transpose of this I, right? So this is the dual problem, okay? And it's called exchange. And it's actually, by the way, there's other problems which are more complicated, have graphs and things like that, but I think you have to understand these two first before you fiddle with the other ones. Okay, so it's a beautiful problem. It's basically, you think of X is a variable of size n, and there are n goods. And then Xi, agent I, sends some goods in to the, either sends goods to the exchange or takes them out, right? Either depending on the sign. And then this condition says the exchange has to clear, the market has to clear. So the total amount that comes in has to balance total amount out for every good. Okay? And then Fi is the cost incurred, or if you want to take a negative, it would be the negative utility derived by agent I, right, for a set of goods, right? So, okay. So this thing is really an equilibrium or a market clearing, and the dual variable is indeed a set of valid prices for the goods. And you could, at that point, you could exchange money or not, or whatever. So just as well to make it a virtual cash payment. It doesn't matter. So, in other words, it's kind of one of the most basic problems in economics. So that's it. Okay. So exchange ADMM is very simple. It turns out to be this. There it is in unscaled form. I mean, it's very, very simple. Or scaled form. It just looks like that. It says that each entity should minimize its private function plus, and then you can even interpret all terms, right? Plus a quadratic penalty. This is what's driving them to clear the market. That's U. And then this one is very interesting. The xk bar, is the average of the x's on the last round. The average of the x's should be 0. That's the constraint. That's the market clears. So xi bar is an interesting vector. If all of a sudden I sent a message to everyone saying, that's it, game's up, time to stop, but we have to clear the market, then what the correct thing to do would be for everyone to add x bar to what they want, whether they like it or not, right? Because that's sort of that's what's left over, and I hand it out to everybody. And sorry, but you have to take a little bit more of this. I'm sorry, you have to take a little bit of less of that, and then the market clears. So this says that everybody should be aiming to clear the market. This is their share of clearing the market, right? So I mean, it's beautiful actually. Okay, that's it. So, but once again, notice the structure. It's a meta algorithm. Every step, the only thing you do is you have to solve, in fact, proximal. That's it. So you just have to evaluate a proximal operator. Okay? So that's it. And so this is a taxonomy process, right? It's an iterative process that identifies prices, if you like. The difference, though, is the following. The original taxonomy process was this. Where'd it go? There's the original taxonomy process was, okay, this. It's this. That's the price update, and you get rid of this thing. Right? And this is what people like Arrow and Ken Arrow and other people did, and that's the most basic one. Unfortunately, it doesn't work, and it's very slow. Right? So it turns out all you need to do, and in fact you can get beautiful interpretation about this. If you add this term in, this is a beautiful thing. It's this one, that's a market term. It can be positive, negative. It could be a subsidy, a payment you make. So this says that like pure unfettered capitals, actually this doesn't work at all, just for the record. I mean, as a practical matter. This says if you add a regularization, which is a social good regularization, or a cooperation regularization, it changes this from an algorithm that works in theory but not in practice to one that works always. Always. So all you need to do is add this regularization, and notice what it is. This says this target is the difference, is actually the point that would have everybody clear the market. That would be it. So it's actually like beautiful, I think. So okay, that's it. Okay, so we can do two things at this point. We can stop. That's perfectly okay. Or we could do an example that has that's on dynamic energy management. I'm totally neutral.
Let's have an example.
Okay. It's like 5 minutes, maybe a little bit more.
We have no example.
Okay, that's fine. So here it is. So the idea is you have n devices, and they're going to exchange power over time periods, right? So each vector is actually going to be a power flow profile for a device, right? So if you have a generator, xi will tell you how much it generates versus time. If it's a battery, a storage device, it tells you how much it charges, discharges over time. If it's if it's a smart load, it tells you how much energy it consumes versus time, right? And the idea is that some are smart and that they can change their profile. That's the idea. And in fact, it's a multi-commodity problem because electricity between 2 and 2:15 p.m. is a different commodity from electricity between 3 and 3:15 p.m. They're just totally different commodities. It's a multi-commodity problem, right? And the problem is that for devices, they link together over time. Okay, so this just says energy has to balance in every time period. And the functions here are the cost. But remember, in fact, we'll see most of the time there's zero cost. It's just constraints you're encoding. Nothing, it's just constraints. And so what happens now is Exchange ADM gives you a distributed method for dynamic energy management. And what's so cool about this is a bunch of devices connect together in a node. They exchange, they handshake, right? And then what happens after that is they exchange messages. Each one privately optimizes its energy profile. And basically they send a message to each other that says, I propose to generate or consume this electricity pattern. They all contribute. They don't even have to know, by the way, who else is on that node. Totally irrelevant. There's something on the node that adds these up. If they add to 0, it just stops. It just says, we've cleared the market, we have a plan. Then it sends a message back to everybody that says, okay, do it. And then you generate 1.3 megawatts, then 1.4, you consume 300 kilowatts, then this or whatever, it all works, right? But otherwise, these messages keep going back and forth until you clear the market. So this is the idea. And what's cool about, and so in this case, the optimization is not carried out in different processes. Well, they are different processes because these processes are on the devices themselves, right? So your refrigerator, you could do this. Your refrigerator could have a separate thing. It's nothing the calculation required for it. I'll say a little bit about that later. Okay, so, all right. So I'll do an example, and it's a baby example, but just to show you how it works. So we have three example generators. You have a big one, like this is the power. Actually, sorry about this. The labels are wrong. That's my fault. Okay. So the labels are wrong. Okay, it doesn't matter. You have a high capacity generator like this. That's the min power max. A medium, and you have a small one. But what they have, each of these has limits, dynamic constraints, and the dynamic constraints are that they can't change power very fast. You can't see it on here, but there are these dashed lines going like this that says there's a slew rate limit to how fast you can change your power. The big generator has a small one. This has a medium one, and the small one, which is like a gas turbine, is allowed to change its power by a lot. Not completely, but by a lot every step. So that's the idea. By the way, these are kind of real constraints. These are the kind of constraints.
What axis?
This is the power. Actually, this is the negative power generator. This is the cost. Okay? Oh, and this is just some examples here of some things. Okay. All right. So a fixed load, that's simple. It's a very stupid thing. Here's a residential fixed load. Here's an industrial fixed load. I mean, I'm just making all these up, so don't worry. And the idea is, here's the cost function. It's really silly. It's this. The cost is plus infinity if you don't exactly match the load. Otherwise, it's 0. This is just to show you that you can have dumb devices as well as smart devices. Okay? So here's a shiftable load. So a shiftable load is a very interesting thing. This is something like this. You need to pump a certain amount of water from one place to another, and you need to do it over this time period, from here to here. Okay? You have a maximum rate, or you have to charge a battery, like for a hybrid vehicle. You want to charge it over some period, and what you're allowed to do now is to shift the consumption. So what is fixed here is the integral, the maximum. The integral of all this is a fixed number. You could do it evenly, you could do it all at the beginning, all at the end, or you could do something weird like this. Okay? And so the cost is very simple. It's just 0, or it's plus, it's 0 if you actually pump the water, and it's plus infinity if you don't. So it's very, very simple. Okay, a battery is completely dynamic. A battery is dynamic and it works like this. This shows you the charge level in the battery. Here's the charge level in the battery. And this is the charge-discharge profile. I guess this is charging. You can see that going up. And then this is discharge here. And this is the idea. And so here's the cost. Again, it's not complicated. It's this. It's just a constraint. So the only thing you have for a battery is a constraint that says, I can make that profile with my limits on everything. Okay? So, okay. I can skip this. And we'll go, here's HVAC. So heating, ventilation, and air conditioning. So here you have a required temperature over a day. The building's unoccupied here. Here it's occupied. This might be something like the outside temperature. And then the rule is that you keep the rule here is that you keep the temperature between here these limits. Okay, and this would be the cooling tower. And actually, you see something very interesting here in this example. If you go down here, all of this building is completely unoccupied. But if you go down here, you're doing considerable cooling while the building is unoccupied. Anybody want to guess why?
To get prepared to the active period?
Yeah, you're going to exploit the thermal mass of the building. You'll cool it when it's going to turn out there's other people don't need electricity here. The price is low, so you're going to pre-chill the building so that when people get there, and then this is weird. This is you taper off. You actually turn the air conditioner off completely before the end here. So this is actually pre-cooling. Right? Of course, that wasn't programmed. That came automatically from solving a convex optimization problem. Right? So, okay, that's it. And again, the cost structure is very simple. It's plus infinity for violating constraint, 0 otherwise. Right? And notice imagine what would have to actually implement this would be very simple. It would mean in your building management system, you just have to solve a QP. A little QP, and you have to solve it every time you get this message from the others. I'll say, okay, I'll tell you how fast it was. To solve the proximal operator for this, it's a little problem. I think this is 15-minute increments, so I don't know what that is, 96 variables. You have some auxiliary variables like the outside temperature and things like that, and the state is the temperature of the building. And so you end up with a little quadratic program with maybe a couple hundred variables. Okay. So, and if you saw, I guess, the first talk I gave or something, the second, then you would know. You could make a guess as to how fast we solve those. Somebody want to guess?
Microseconds.
Yeah. By the way, it's not 5 microseconds. I have to tell you. In fact, this may even be up at almost a millisecond. Yeah, I forget what it is. It's 100, it's 300. It could even be a millisecond. I don't know. But if it's a millisecond, it's not a lot more than a millisecond. Okay, so so this is just a new regime where you have to. Okay, I'll skip that. And we'll just go to the example. So the example is we hook 10 of these things together. In fact, what we hooked together are all the things we just saw. We just hooked them all together. And in fact, what we were showing you is, so here's 80 mm. So these are the optimal. That's the optimal power, right? Like that. If you're wondering, what is all this weird stuff? It's because remember, there's these weird industrial loads that click on. There's the building all of a sudden is occupied, and there's a battery. There's people charging their cars. I don't know. There's all sorts of crap happening, right? All of this combines. There's some farmer that wants to pump water. I don't know. Okay, so all right. So on the first iteration, here's what the generators do. Nothing. They're just off. Because they haven't yet, actually, because basically what happened was for the generators, the prices were all 0. And you told the I sent a message to the generator saying, oh yeah, the prices are 0. How are you going to generate today? And the answer is, I'm going to either be off or turn off. And this one was off. This one, they all turn off as quickly as possible and stay off. Okay? The residual, you don't even see on this. This is the residual. Of course, the residual is huge because other people are using power, but no one's generating it. So the residual is huge up here. Okay, so that's it. This is ADMM. Okay, now you do, this is 3 steps. And in 3 steps, the prices are getting closer to what they should be there. And all of a sudden, the big generator is waking up and saying, okay, I'll generate something. The medium says, okay, I'll generate something. And the little one is kind of making up for the fact that the big one is still asleep. That's what this is. Yes, it's over-generating here. And the residual, you know, I'm really irritated because I think this residual, that's like 0.1. But that's all, this means that's 1%. So it means that this is like a few percent. In 3 steps, you're within 3% of clearing the market. This is 5, and I'll just keep going, 10, 15. At 20 steps, this residual, this is 0.0, that's 0.1, minus 0.1. The numbers involved are 10, that's 10. So this is 1%, this is way sub 1%. This is far more than you would need to do this in practice. In fact, solving better than this makes absolutely no sense, right? But this is the idea. So there you go. And there you have it, sort of converged. Okay, so there it is. We'll go back. There it is. So, well, what I find kind of cool about this is actually to think about the message passing that happened. 10 devices, all weird, 3 generators, like a battery, somebody trying to charge their vehicle, somebody trying to pump some water. They all connected together. Not one of them has any idea what the other devices on the network is. They don't even know how many there are. Not one, right? Each one supports only one simple protocol, which is they get the prices and they get the residual. It's primal. This method is primal dual. You don't just get prices. You get the price and you get the residual. And then each one solves locally a quadratic program, in this case, because the constraints are all linear. Linear and the objectives are quadratic. It doesn't matter. Each one then solves a small QP in, at most, a couple hundred microseconds. Each one solves that. That small QP couples a couple of things in it. It's basically, it's the traditional economic incentive, which is if that's the price, and I can generate at a lower marginal price, I'm going to generate. Or if that's my consumption profile, I'll shift it towards where the prices are low. Okay? This is all obvious. But there's a second term, that's the key to this whole thing, which is the social good one. Which is at the same time, I'm going to skew myself towards doing my share to clear the market. Okay? So I find the whole thing quite interesting. And this we've implemented, last month we ran this on a network with 30,000 devices, something like 80,000 transmission lines, and we got a problem with about 500 million. It's a convex optimization problem with 500 million variables. And we solved that in about 6 minutes on a single machine with 8 cores, okay, with multi-threading. So, and by the way, you could divide that number by anything you like. You just give us more cores, right? Because what we did is you just make a queue, make a thread pool. You have a queue of all these 300 microsecond things that have to get solved, and whenever you just we didn't even do anything. The operating system migrates the threads across them, and it balanced and anyway. So, all right. So that's the idea. Okay. So I'll just finish up. All right. So here's the idea. You can say ADMM if you like, but I actually mostly now go around and say operator splitting. So because you shouldn't just say ADMM. It's it's identical to Douglas Radford splitting, right? So it's the same as, it's identical to, or closely related to lots of methods, other names. It's been around since the 70s, but in fact the ideas go, it's identical to an algorithm that was developed in the 50s for something completely different, for solving PDEs. Okay, so here's what's amazing about it. It gives simple single processor algorithms that can be competitive with state of the art. I showed you some of those, like a 6-line lasso solver and a 6-line covariance selection solver, right? 10-line, whatever it is, right? But the really interesting part is that it gives you a completely transparent pathway to modern computational fabrics, right? So you can go from single thread to multi-thread, multi-core, and then just almost with no change, right? you can go to an MPI system with 32 cores, or you can go to a data center with 50,000. So I think this is the really cool part. And I should give you a little bit of a warning on that, just so that I've been honest. So some of this was tried at Google on things like million core things. And the infrastructures for these things are just not there yet. They don't have state. All sorts of terrible things happen. And so only one of them actually sort of works, but these are infrastructure systems issues, and they will. So if you go and try to do this with MapReduce or something, you're going to be deeply disappointed. But the hope is that within a year or two, there will be large-scale open source systems for data center type stuff where you can actually do this and it will work. Or I guess the correct way to say it is, it doesn't work now. So it's not for a mathematical reason, it's for a silly systems reason.
And what are the problems with MapReduce?
It's stateless.
Stateless, you mean that you can't track that now you alter your vector?
Yeah, well, no, what it is something like this. This idea is very much in this kind of like 80s style thinking, where you have your data, you have your data, you have your data. And that's not the way MapReduce works. It's stateless, so what happens is a giant set of jobs. The reducers solve the optimization problem, but then all the data is moving all over the place. There are ways to do things like hint to the scheduler that this data should be near this processor, and that makes it better. But otherwise, it ruins the whole thing, because the whole idea of it is that you have these processors sitting there, and we're exchanging small messages. That you have 100 gigabytes of data behind you, and then you and I are just exchanging small messages. And the problem that doesn't work that way in MapReduce. There's a single distributed file system, and it's a kind of a disaster. But they know it, and people are working on it.
That's one. And for what problem do you try to use this stuff?
What's that?
For what specific applied problem you try to use this stuff in Google? Or it's
Oh, actually, I found out a few weeks ago it's actually now being used at Google. So,
no,
it's not in any production system, but it's being used. Yeah. These are for machine learning.
No, I mean just
machine learning.
What kind of experiment?
Machine learning. Click predictors.
Click prediction.
Click predictors.
Just to classify.
And well, the other one they're doing it for is resource allocation. So advertising resource allocation.
Okay.
So, and I only found out accidentally 2 weeks ago because somebody accidentally included me on a CC in an email, which I probably wasn't supposed to get. So, all right. Good. I think that's it. I'm done.
Okay. First of all, you promised to say a few words about how to choose rubber.
Oh, yeah. Okay, yeah. You have to ask that. Okay, so the excellent question is, how do you choose row? Okay, and I will start by telling you the honest answer. You ready for it? We have no idea.
The same with organization.
What?
The same with organization statistics.
Right. So it's something. No, in statistics you can. No, in statistics that's not true. I would say you do by cross validation, and you could never argue against that, right? So I would say actually it's much worse than that. Although you could do the same thing here. You could say you choose row, you fiddle with row until it works well, but that's actually ruins the whole story. Because the whole idea, look, if you're doing optimization, and the old style optimization is you twiddle with the parameters until it works. But the whole idea is these days it's going to be embedded in applications. And you cannot have somebody fiddling with the parameters. Okay. So now that I've admitted that in fact we have no idea how to choose row, there are some heuristics that people use. And there's a simple one that actually goes back, I think, to the 60s and 70s, which basically increases or decreases row to try to make the rate of convergence of the primal and dual variables about the same. Okay? That seems to work okay. My students have come up with an extremely obscure update rule that has like an X in it and something like that. That it's going to be like the Merotra rule, right? Which is, like it came from outer space, no one knows, you have a vague idea of what it is, and it works really well. And this method seems to work very, very well. This one they have. Now the other weird thing is this. When your data is scaled properly, don't ask me why, but it seems like row equals 1 seems to work very well. But I should emphasize we have no idea.
Okay, so question please.
And are any estimations of the rate of convergence using which we can sum?
Oh, yeah, okay. Great.
Depending
Okay,
on
great. Okay, so, yes. So what's the rate of convergence theoretically? I can tell you exactly what it is. It is the worst there could possibly be. The subgradient method is 1 over epsilon squared to achieve epsilon accuracy. This is also 1 over epsilon squared. And for the same reason. In fact, to prove convergence of its identical, the Lyapunov function you use is in fact the distance to the it's the distance to an optimal primal and dual point, which you don't know, right? So, and then it's the same as subgradient method. There's something that's summable. And then if I ask you if something's L2, what's the rate of convergence? You get 1 over epsilon squared. So, having said that, I would like to point out the following. You've seen here that the cost of an iteration can vary over 1,000 to 1 range or more. And in such a circumstance, I think that the number of steps required to solve a problem has much less. I mean, so we were very worried about this row issue. Very. Until we started solving a lot of problems. When we started solving a lot of problems, we realized that with factorization caching, for example, when you get 1,000x or 100x or 10,000x discount on iterations after the first one, it turns out it doesn't matter if it takes 20. If it takes 20 iterations or 2,000, hardly matters. So it's a secondary thing. By the way, I would still love it if someone were to figure out what the correct row is. That would be a huge advance.
Yeah, actually, for some particular problems, there are some ideas, say, for smooth functions.
Oh, I'd love to hear about it.
Geometric rate of convergence and.
I'd love to hear about it.
But it doesn't help in real life.
Yeah, because see, but the problem is that we run it all the time with these things which are indicator functions, and you have no concept of curvature. We don't know anything.
Sure. No.
So can we see page 34
Sure.
to begin with?
There we go.
Oh, 38, sorry, 38.
So
Here is consensus. Yeah.
Great.
Do you know that another name of this problem is choosing the level of public good?
No.
Because I just building the bridges because initially there are some results for this problem going to year 77. Its name's Groves Ladiat initially. Oh, I write down examples who applied nearly the same approach to solving it. The economists that know nothing about.
That's great.
Yeah, and now there is a whole bunch of study concerning these problems, all going around, say, the last at square, and the whole theory, which name is supermodular mechanism design. I also can mention. It's very interesting because there are a lot of discussion about the value of rho and what should be announced exactly xy. And
Fantastic.
yeah,
So
it's interesting.
I wish.
Unfortunately,
we also published this thing like last year, but I wish I'd heard this beforehand.
And also, I have a question about Gas and Map protocol.
So, and you're gonna send this to me by email.
Oh, okay.
No, you have to.
Yeah, for sure. I promise you.
It's too late for this, but from now on, I will explain. Actually, we asked our economist friends.
Am I right that
and they said no, they didn't know of any such thing, so I'm not surprised.
it's a vast field? Yeah, you see, and am I right that Gaussian map protocol means that Fi value of value functions may be private?
That's exactly right. Exactly.
You see, this is also the result.
Yes. Right.
It's very rich and very important interpretation.
Exactly.
Because you see, the initial problem was that we know how to solve such consensus problem, and the solution is so-called Lindahl Lindahl allocation. It's
Okay.
the same. But the problem was that each agent was motivated to don't tell true about
Yes.
its own Fi.
Exactly.
You see?
Right.
And such approach allows just
Yeah.
to
Right.
exchange by messages of X.
That's exactly right.
Yeah.
And you never reveal your F.
Yeah, and there is
No. Exactly. So yeah, so I talked to my friends at Stanford who do mechanism design and things, but frankly I don't understand them when they say anything.
yeah.
But I don't think they said anything intelligent like this, so I wish I had talked to you. So send me email about this.
Okay.
Because then I'll go back to my colleagues and
Yes.
say, look, there is this thing. That's great.
Okay, good.
Yeah.
Yeah. Well, what about huge scale, something like that, when we have a of x and x is of huge dimension?
No problem. We split X up.
But what about the theoretical convergence or rate of convergence?
I told you it's the worst. It's the worst. It's the worst there is, right? The worst rate you can possibly have is 1 over epsilon squared.
But
That's
it works.
But it works. That's true. No, the one thing I can say, and is actually true, is it works. Eventually. Yeah. So I think if you're interested in complexity, this is of no interest whatsoever. No, I think because the rate is the worst there possibly could be. So.
Okay. Okay, great.
Okay.
So thanks again. And maybe I'll say a few words in Russian because some stuff maybe people are not that familiar with. Вот говорилось, что впервые такого рода идеи расщепления появились при численном решении уравнений с частными производными. И это было действительно так, потому что это была ситуация, когда впервые стали решать задачи очень большой размерности для совершенно практических нужд. И там вот придумали метод, который называется метод переменных направлений Дугласа Рекфорда. И это было действительно еще 50-е годы. У нас в Советском Союзе этот метод тоже активно применялся в разных модификациях с разными именами, но это действительно была впервые реализована идея, что называлось сплитинг, расщепление. Большая задача разбивается на вот, примерно таким образом на куски и решается вот, каждая эта частная задача. Ну, кроме того, конечно, теперь вот сам этот метод обобщенных функций Лагранжа, он действительно возник в конце 60-х годов, в начале 70-х, когда вот появился этот квадратичный член функции Лагранжа. И для него в чистом виде есть много результатов о сходимости, о скорости сходимости. Но здесь одновременно к этому добавляется еще идея вот этого расщепления, поскольку когда мы вводим квадратичную функцию Лагранжа, вот это свойство сепарабельности, что переменная у нас независимая, оно теряется. Так что вот тут как бы основные идеи происходят действительно из разных источников. Ну, вот замечательно, что это дошло уже до решения совершенно грандиозных задач, невероятных размеров. Okay, so Steven, thank you for very exciting talk. And you know, actually we met this method for some particular cases. For instance, we dealt with problems like Lasso, L1 optimization. Pavel, you remember? And particular cases. We used it in various forms and so on. Actually, many years ago in our laboratory was a PhD student, his name was Kibarden, who solved problems like sum of functions, and so let's minimize each function independently and then average in some way the results. It was at the beginning, the middle of 70s. Okay. Okay, so thanks again.